Okay, so in our addition reactions, specifically with our hydration and hydrohalogen, yes, hydration and hydrohalogenation reactions, we see selectivity in our reaction. So, for example, if we take this alkene here and do a hydrohalogenation reaction, we could potentially have two products. Specifically, one where we have the hydrogen added to the same side as the rest of the hydrogens, and the chlorine added to the side with less hydrogens, or the opposite. However, this particular isomer, constitutional isomer, is not formed. So the question is why? Why do we see only one isomer and not the others? Wouldn't you think you would get a 50-50 mixture? So in order to determine why we get one over the other, we need to consider the mechanism of the reaction. So mechanism in like mechanics terms is like how something works, right? So a mechanism in organic chemistry is curved arrows that show the movement of electrons. So we're talking about how does something work. So if we're looking at the mechanism of hydrohalogenation here, I'm going to just be using the highlighter and the laser pointer in order to show all of this. I kept everything drawn in on here so you guys had a very specific and clear example of all of this and didn't have to write it because we're not going to be doing too much mechanism work. So a mechanism shows the movement of electrons. Electrons are what makes up bonds, right? A covalent bond is two electrons that are shared between two atoms. So by showing the movement of electrons, we're showing how the electrons move to form new bonds. So in a hydrohalogenation reaction, we have here our acid, that is our halogen, so HX, or in this case, HCl. And we have our double bond. So the two of the electrons in this double bond, so we're specifically talking about the second bond, not the first bond. Those two electrons are going to decide like, hey, yo, I want a proton because the protons have less electrons, right? So where there are electrons wants to grab things that have no electrons. Positive and negative charges attract. So the hydrogen has less electrons, kind of. And so it's going to take the hydrogen, and when it takes the hydrogen, the two electrons here in that bond are going to be kicked off onto chlorine. So now chlorine turns into, let's go onto the top up here. Chlorine then gets its two electrons. So if I had my Lewis dot structure here, there's 6 electrons in lone pairs on chlorine originally, but I'm going to take the bond and put them both onto chlorine. So now chlorine has 4 lone pairs. It's got all 8 electrons on it. However, when I took away the multiple bond in the alkene, that meant that I had a hole here. There weren't enough electrons on that carbon, so it leaves a positive charge. Okay, then that chlorine is a negative charge, and the positive charge on the carbon, they are attracted to each other, positive and negative attract, and so they come together. 2 of the electrons on chlorine fill in that hole where that positive charge is, and it forms this product here. So the same exact thing could happen. So we went to the top row in which the hydrogen went to the side that has less hydrogens, and it made this intermediate here. Or we could do the opposite. The hydrogen could just add to the other side of that double bond and make this intermediate. And then the same thing, that chlorine with all of its electrons will add in to where that hole of electrons is and make this one. And we see that we have a favored and an unfavored selectivity of products. So what we have learned is through a lot of experimentation in the lab is that selectivity is determined by the stability of the carbocation that is formed in the first step. So a carbocation, let's use our highlighter to be specific. Carbocation is this here. So where we have a cation or a positive charge on our carbon. Carbo meaning carbon, cation meaning positive charge. So we're going, based off of how stable these are relative to each other, is going to tell us which one is favored. So on our next slide, we talk about carbocation stability. So more substitution makes carbocations more stable. So a methyl group, for example, only has 0 substituents, right? We just have hydrogens. We don't have anything different. So it is very unstable. But if we have 3 methyl groups here, like in the one that I have labeled tertiary, that is the most stable. It has the most stuff around it, and therefore it makes it the most stable. So we are going to look at our 2 carbocations that we formed. So we have this one here and this one here. So in our first one, we have one, let's do a different color. We have one side that has something on it, a substituent, but only one. So that's called a primary carbocation. Okay, and this other one, we have 2 sides of that carbocation that have substitution. Therefore, it's secondary. The more things around it, the more things off of that carbocation, the better and the more stable. So more stable intermediates are more likely to be formed. So that leads to the major product, or the product we actually form. So this molecule, the second one with the secondary carbocation, is more stable. This one here is less stable. All because of how many things are off of that carbocation. So the more stable the carbocation, the more likely that product will form. So this is telling us that when we go back to our mechanism on the previous slide, when we put the hydrogen in the first step, so in our first step, we add our hydrogen in. We add the hydrogen to the side that has more hydrogens, because then the side that has more stuff on it that's not hydrogen has the carbocation. That carbocation is more stable than the one on the side with more hydrogens. So this is a more stable carbocation, and therefore it makes the favored product. That's a lot to get through. Take a moment, think about it, rewatch this video a couple times, but we will practice this in terms of practicing the selectivity of these reactions in our next video.